Hello everyone, my name is Stefano Ruffini from Calnex, and together with Silvana Rodrigues from Huawei, we have prepared an introduction dealing with the distribution of synchronization over the packet layer of networks, both frequency synchronization and time synchronization. After a short introduction related to frequency synchronization delivery, most of the focus will be on time synchronization. That is particularly important for the operations of various applications and networks, and offers certainly more challenges if compared with the delivery of frequency synchronization. So let's start with the topic of frequency synchronization delivery via packets. The fundamental principle of the delivery of frequency synchronization via packets, such as periodic PTP sync messages, is to look at the frequency of the arrival times of these packets and make use of it to recover the timing of the clock that has been used as a reference for the synchronization network. Typically a primary reference clock that can be implemented using a local reference based on a season clock or a GNSS receiver. The issue in this case is that packets that are carrying these messages can be impacted by packet delay variation that is created by the buffers of the routers or switches in the packet network. This is the reason why the PLL of the receiving clocks implements some pre-filtering of the packets that can be used to control the PLL in order to remove those packets that have been significantly impacted by PTV. And as shown in this example, for instance, one potential solution is to look at the packets that have been delivered with a minimum delay, because those are typically less impacted by packet delay variation. One important example of a standardized architecture and methods to deliver frequency synchronization via packets is provided by the ITT telecom profile in G.8265.1. In this case, you see that you have a time transmitter clock that delivers periodic sync messages, PTP messages, down to the receiving clocks at the output of the network. Packet network does not process those PTP packets that therefore are impacted by packet delay variation. And that's why, as I mentioned before, it's important that the clocks that are receiving these packets implement some pre-filtering. There are various recommendations related to this architecture, like G.781.1 that provides the synchronization layer functions, 8263 that provides the clock specification. Let's now move to the time synchronization part of this presentation. A good reference related to the delivery of time synchronization is provided by a number of ITT recommendations that have been delivered over the last 15 years by study group 15. In particular, G.8271 provides the general methodologies and architectures and requirements related to time synchronization. And as shown in this slide, there are two main approaches that can be used for the delivery of time synchronization. The first one is to deploy, for instance, GNSS receivers locally directly connected to the end application that requires time. A second option is to have this synchronization primary reference at the top of the synchronization chain and then distribute the timing reference across the network via packets, typically precision timing protocol packets as specified by 1588. And you see here across a network where the transport nodes may also process these packets. Of course, in the end, what typically is deployed by network operators is a combination of these approaches, where, for instance, a local GNSS receiver could be complemented as a backup by a reference that has been distributed over the network. When time is delivered via packets across the network. It's important to also estimate for the transit time, the transit delay between the synchronization reference and the receiving clock. And to do that, the typical solution is to make use of two-way timing protocols. PTP or NTP are typical examples. And then what is done by evaluation of the round trip delay by making the assumption that the channel is symmetric, it is possible to estimate the delay it takes, the time it takes the message, the timestamp to transit the network. Obviously, the assumption for a symmetric channel is very strong, and this is one of the main issues that we find in networks in the delivery of time synchronization. Any source of asymmetry will result in a time synchronization error. Continuing with the example from telecom, the time synchronization architecture is provided by G.8274. And this recommendation presents various aspects related to time synchronization architecture. You can see here, for instance, the overall network reference that from a packet time transmitter that gets reference from a primary reference time clock. Basically, the primary reference time clock is a clock that is defined in G.8272 and G.8272.1 that keeps track of UTC reference within certain performance objectives. As an example, enhanced PRTC, that is the best PRTC reference, is able to provide holdover over several days with performance within 100 nanoseconds. From this primary reference, the timing is then distributed across the network, where there can be clocks as defined by IEEE 1588, boundary clocks and transparent clocks, with performance objectives defined by clock specification such as G.8273.2. And then this reference is forwarded down at the end of the network to the end user, that can be, for instance, a radio base station. Very often the packet layer that is responsible to deliver PTP messages is combined with the physical layer that can be used to deliver frequency synchronization. And this combination has been found very useful, for instance, to improve the stability of the clocks, or to provide a kind of holdover. So when a PTP network presents some failures, the time synchronization could be maintained by the accurate and stable frequency synchronization delivered by the physical layer. In order to use PTP to deliver synchronization, every industry has to define its own profile. In this way, all the options that are specified by 1588 can be clarified, what options are used, what are the ranges for the different values, and so on. In case of telecom application, the profile is specified by G.8275.1 for the case of a network where every node supports either boundary clock or transparent clock. And there are a number of recommendations that are also related to this approach, for instance, specifying the clock performance like G.8273.2 or G.8273.3. And G.781.1, as I mentioned before, is providing the frequency, the packet layer synchronization function. The end-to-end performance and the network performance is specified in G.8271.1, where starting from the end-to-end requirement, for instance 1.5 microseconds required to support 5G networks. It has been possible to specify the performance of each node, 73.2 and 73.3, and based on that define reference networks that can be deployed by network operators that can in this way guarantee that performance is met at the end of the network. You can see in these examples, for instance, that in order to meet 1.5 microsecond, a reference network of 20 or 10 clocks, depending on the characteristics of the clocks. You see there are different classes of clocks that have been defined with different performance objectives. For instance, class C with time error, constant time error within 10 nanoseconds is particularly important in front-haul applications. Front-haul applications are presenting some tight requirements in terms of relative time error. You see in this second example a setup that is typical in front-haul where we need to control relative time error between the accuracy, the time synchronization that is delivered towards the cooperating radio base stations. So you find in 71.1, in addition to the end-to-end requirements, you can also find examples of and guidelines on how to build the networks in backhaul or in fronthaul. I mentioned before the profile where every node in the network is able to support PTP, either with a boundary clock or transparent clock. However, there are cases when this is not possible. For instance, when there are leased lines or in case of legacy hardware already deployed in the network that does not support 1588. Due to that, a second profile has been specified by I2T, the so-called PTP profile without timing support from the network, and this is specified in G.8275.2. And as part of these studies, in 8271.1 it was also provided the requirements in terms of packet delay variation that can be acceptable in those networks. You see here there are two main setup for the partial timing support, the so-called assisted partial timing support, APTS, where the assumption is that there is a local time reference, like a local GNSS, that in normal operation is providing the timing to the end application, like the radio base station, while the PTP over a network without timing support is used as a backup. A second approach is partial timing support without any local GNSS, and there are different requirements depending on which use case is being considered. So because there can be multiple profiles, in particular in the same network there could be segments that are using the 75.1 profile and other segments with the 75.2, it has been required to define also an interworking function that make it possible to connect these two segments of the network. And details can be found in G.8275. I have spent most of this presentation looking at the examples from the telecom networks because I believe the related documentation, the recommendations provides a very detailed and informative material for the topic of time synchronization. However, it's important to mention that there are several industries making use of PTP and that needs the delivery of time synchronization, where you can find very similar concepts. For instance, for the power applications, you find profiles in the IEC /IEEE 61850-9-3 that essentially provides similar requirements as we have seen for telecom, with the requirements with the target of 1 microsecond and with some reference networks, in this case with up to 15 transparent clocks or 3 boundary clocks. also with the requirements for the performance of each clock and so on. In this case, the profile is based on peer-to-peer delay messaging. Is different from the telecom, where instead it is based on the delay request methodology. There is another profile specified by IEEE for the power application, the C37238, which can be considered interoperable with the previous one. Another interesting application of the PTP protocol is what has been done by the White Rabbit project, and that is now part of the profiles, default profiles defined in IEEE 1588, in particular as Annex J.5 of the 2019 version of the standard. And this profile is targeting very accurate delivery of time synchronization in the sub-nanosecond level by making use of special solutions, particularly by compensating any source of asymmetry, and also having implemented very accurate timestamping solutions. So this profile was, as I mentioned earlier, part of a White Rabbit solution defined by CERN, and now is part of a standard default profile of the IEEE 1588. Another important example of a PTP profile is what has been defined by IEEE 802.1as. This is a profile that is important for applications such as audio, video, automotive, and industrial automation. There have been several releases. The first one was in 2011, and the second one in 2020 was extending the field of application of the profile. The first one was really focusing only on audio and video. And one particular aspect of this profile is that it has defined a kind of a hybrid clock that is in between a boundary clock and a transparent clock. It's a boundary clock in the sense that participates in the best master clock algorithm, but is not required to recover timing. So essentially, it works as a transparent clocks, just updating the residence time. Recently has been released a further version in 2025 that is including several amendments that have been developed over these years, in particular enhancing aspects in terms of redundancy with the new hot standby function, but also improving performance with the rate ratio operations. This is a way to keep track of frequency differences in the clocks in the network, so to improve the recovery of timing. As related to industrial automation applications, there is a specific profile for that makes use of 802.1as I mentioned before. This is the IEC/IEEE 60802. It's a project that is being completed in this period, and as I mentioned, it's based on 802.1as. It implements some enhancements in terms of adding some information on the rate ratio in order to improve the accuracy. In fact, the target performance is quite challenging, because the target is to meet 1 microsecond over a network of 100 nodes, and due to that it was required to implement some enhancement to the 802.1as. Before concluding this presentation, I'd like to mention a couple of important initiatives that have been done in the last few years to improve the accuracy when timing is delivered across specific network interfaces. In particular, Amendment 802.3cx from 2023 that address the need to minimize the impact to the accuracy due to certain Ethernet functions like alignment markers and so on certain interfaces. And then the Mobile Optical Pluggable Alliance initiative with technical reports that address the need to minimize the impact of impairments to time error when there are specific optical interfaces used, such as PAM4 interfaces or coherent optical interfaces. Essentially, the principle is to define some limit to the performance of those optical modules so that can be used by system vendors in order to meet certain requirements. So we are at the end of this presentation. As part of the material in the PDF slides, you can find much more details, and I hope you have found this interesting, and I would like to thank you for your attention.